Hi, my name is Chris Schaffer, and I'll be walking you through my final project for CSC 578. I did the Kaggle project, which many of you already are somewhat familiar with, so I won't go into too much detail of that competition. But the idea was to predict a set of test temperature data from a set of training atmospheric conditions as well as past temperature data, shown here in the dark red. Test data is here in the bright red and shown in a little more detail here. So my first step, aside from the trivial library loadings and reading in of the data, was to expand the data and extract as much information as possible. So not every variable contributed something informative like seconds and minutes, so those were dropped right away. But what had meaningful information in it is output here, and we can see it here as well. This is the original, and this is the expanded data set. So for a little bit of visual feedback and just getting a grasp of the data set, I used a scatter plot matrix here. Uh, and the idea is to look for the most linear or at least linearizable relationships between the target and the rest of the variables. So the target data or target variable is the second row, second column here, by the way. So correlation matrix was also a really good visual tool, just at a quick glance to see how many of these variables would be useful or informative or related to one another. As we can see here, some of these should just be dropped because they don't really contribute much information at all, especially to the variable we're interested in. So obviously we visualize the training and test data down here, which I think is incredibly important to help you get you familiar with the data that you're going to be working with. The pre-processing step, let's see, okay. So this involved transformations and picking and choosing variables. So I did a mix of forward and backward selection just to see what would help out, and I settled on a much smaller set of variables than the expanded data set. We can see the header here for those. And this is after the transformation, all these values. So I mostly use logarithmic transformations and min-max scaling, and we ended up with a scatterplot matrix looking like this. Again, the second row, second column is what we're looking for, and a lot of these relationships seem to have been effectively linearized, minus some outliers. Here's the correlation matrix of the reduced data set and the numerical representation thereof. Uh, in this cell, we create the training test splits. I won't really go into that since, again, it's all covered online. And then the actual model building. So for mine, I chose to do an LSTM neural network. I found empirically that 80 LSTM nodes seem to produce good results. And likewise, having a larger dense layer here allows for more permutations of different combinations of LSTMs. Um, and the linear activation helps capture as much of the variance from those as possible. And then we have some dropouts to help with overfitting. As you see, I've used 200 epochs to train this. And the TANH activations were implemented to help smooth out some of the more drastic predictions, especially since I didn't do my due diligence and go ahead and remove outliers and change values, etc. So I use the mean absolute error as the loss function because we're fitting one curve to another. We can over or undershoot, so that's something we should be cognizant of. The mean squared error could have also worked, but just from trial and error, I found mean absolute error seemed to give me better fitting results. Likewise, Atom wasn't necessarily always the best, but it was the most reliably consistent at getting low total absolute errors, so I went with that. I found AdaGrad also worked. And then the other big key here is I chose to train or fit the model on only a subset of the training data. So I picked what I felt looked the most similar to the test data. So like we see here, for example, there's some dips that aren't very characteristic of this exact curve here. So I got rid of those and actually improved my model performance. So I think some of this just kind of contributed noise that wasn't useful in the end. And then here is how I compared my models. I calculated the sum of the total absolute error I apologize for the poor naming, but this was really useful for comparing the fit of one curve against another. And then likewise, for training feedback, I used an error versus epoch curve to make sure that I wasn't overfitting at all. So far, it's very difficult to overfit actually. Um, Here's a distribution of the error, not the absolute error, just the error, so we can see how far under or over we are typically. This is really good because we're at about 0. And then here visualized are 3 different scales of actual versus predicted data. The predicted is in red, actual is in blue. And I use the different scales because you don't necessarily get the same resolution or amount of information from, say, this graph that you do down here, where you can see some deltas of half to a full degree. And these were really useful for making sure that the model didn't lag too much or was offset too much in its predictions. And then down here we have the usual clerical stuff like writing, saving, and loading. Um, and so, yeah, along with that, I'll be submitting my report here, which goes into everything I've covered in a little more detail. And I appreciate the time. Thank you.